A dam is a hydraulic structure for a hydraulic structure built across a river to create reservoir on its upstream side for impounding water. You should already know this for various purposes such as irrigation, for municipal or industrial usage, and the supply water. Sometimes you can talk about hydropower, recreation, and so on. So, as already shown in the previous figure, you impound water for various purposes, and the dam actually, in fact, the dam and reservoir complement each other. A reservoir is normally used when you're talking about the main purpose is to impound water for maybe irrigation or for example for cattle usage during drought, or you want to just keep water for usage when there is no the water supply is not good. But dam is used when you are referring to hydroelectric generation sources. So dams are generally constructed in the mountains and mountainous reach of the river, where there is narrow and the foundation is good. I think we already talked about this. The dams are probably the most important hydraulic structure built on rivers. These are very huge structures, so thousands of workers and engineers work for a number of years to achieve this. And generally, a hydropower station is also constructed or near the dam. Of course, because you need lots of water. Hydroelectric power is just water. We harness the energy that water has. So these are very huge stacks. Then generally, a hydropower station is constructed near a dam because you need lots of water and you need to harness the energy that the water has to develop hydropower. Sometimes a pickup weir is constructed on the downstream of a dam in boulder ridge or alluvial ridge. Now, please, those who want to join, I've left a lot of time. Now, people keep wanting to join the class, and we wasted a lot of time. So, I think we need to agree that after some point we will not be able to admit people, so that there has to be some discipline as well. The internet has some challenges, and with all these kind of disruptions, we may not do a lot. So, sometimes a pickup weir is constructed on the downstream dam in the boulder ridge of the alluvial ridge. Now, dams can be classified according to different criteria. The first one is based on the function. We have storage dams. These are basically for conservation of water. These dams are constructed to store water during rainy season. When there's a large flow in the river, the stored water is utilized later during the period when flow in the river is reduced and is less than the demand. The water stored in the reservoir is used for a number of purposes such as irrigation, hydropower, storage, dams. The most common type of dam, and in general, the dam means storage dam unless qualified otherwise. So, by default, if we say dam, we're talking about a storage dam unless qualified otherwise. So the first category is for storage. Then there is what we call detention dam. Detention dams are constructed for flood control, basically. So if an area is prone to flooding, then you need to protect people. Probably it's a low-lying area. So because the flooding usually because there is excess water. So you create some impounding structure where water can be contained. When the overflowing water can be obtained in that place to keep the rest of the area safe for people to live in. So detention dams are constructed for flood control. A detention dam retards the flow in the river on its downstream during floods by storing some flood water. Thus, the effect of sudden floods is reduced to some extent. The water retained in the reservoir is later released gradually at a controlled rate according to the carrying capacity of the channel downstream of the detention dam. Thus, the area downstream is protected. So, for example, I think in the previous years there were a lot of issues in Budalangi, for example, or in Nyakach, I believe. There was a meme. Is it a meme? Of a lady from Nyakach saying Serikali's idea, because every time it was raining, floods used to happen. So this is, you can do a detention dam, because this is during the rain, there is excess water in the river. So of course there are other measures that can be taken. For example, you can dredge the river, because probably alluvial there's deposits of alluvial in the river. So when more water comes, it overwhelms, so it goes out of the channel of the river. So apart from that, you can do a retention dam where excess water is contained and then released at a controlled rate, such that people's lives are not in danger. We have diversion dam. Diversion dam is, for example, you have a project, you are doing a bridge, for example, and the water the presence of water during the construction would interrupt the process. So you do a diversion to keep off, or to keep water off the channel, so that your activity can continue. Excuse me. So that activity can continue the construction. Once you finish, you restore the water back to the channel. So uh, diversion dam is constructed for the purpose of diverting water of the river into an off-taking channel or conduit. Diversion dam is usually of low height and has small storage reservoir on its upstream. Excuse me. The diversion dam is a sort of storage weir which also diverts water in, and has a small storage. Sometimes the terms of weir and diversion dams are used synonymously. So that's it. And then we have the fourth category is debris dam. A debris dam is constructed to retain debris such as sand, gravel, and driftwood from flowing in the river. The water after passing over the debris dam is relatively clear. So, in fact, the dams, most dams, especially for example for water supply, there has always been complaints that the capacity of water supply dams and Dakaini and all the sorts that are reducing, and one of the problem is siltation. By siltation, from upstream, from the debris carried, the alluvial, the cells are deposited in the dam, and this reduces the capacity of the dam. So if the dam, for example, can carry 600,000 liters, the deposits will maybe reduce to 400 or something like this. And this is a big problem. So what you can do a debris dam upstream before you reach the main dam. You do a debris dam, and the debris dam, its function is to kind of allow gives an area for this cells, the sand, the debris basically, or even wood carried, so that they are deposited in this debris dam, so that the water going downstream is relatively clear. And this can also try to contain siltation, which is a big problem with our dams as well. Then we have coffer dams. These are actually not a dam in the sense. It's constructed around the construction site to exclude water so that the construction can be done in dry. A coffer dam is thus temporary dam constructed to facilitate for facilitating a construction. A cofferdam is usually constructed on the upstream of the main dam to divert water into diversion tunnel as during the construction of the dam as shown. So you can see cofferdam and diversion dam are kind of related. Now don't confuse. Cofferdam is you want to keep water away water temporarily. You need to work very fast, and then you can resume. You can restore water to the channel. Now a diversion dam. In fact, this is a question to bring in the exam. A diversion dam is constructed to divert water from the channel. For example, if you go to where is it? Um, the hydroelectric power near Kisumu. What is the name? Anyone? Is it Odino? Hello? 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 The power, is it is it Odino Falls or where? The one around Kisumu, Nyakach there. Odino, yes. The because the course of the river, there is no, because you need height to produce electricity. You need water falling from a great height, but in the natural course of the channel, that was not possible. So they had to divert uh, the the water to a channel where there is enough height. So when water drops from that height, you can generate a reasonable amount of electricity. So this is what we are saying. You divert actually, if you go to Odino, the natural course of the river is not starved, because in fact that's also against, if you divert all the water from the natural course of the river, that would be a riparian illegality. Actually, it's a big issue because the riparian law does not allow that. So you still allow some amount of water in the natural course of the river, but you divert. So, for example, the Odino one is a diversion dam, in fact. So the water goes through some place where we can get enough height to generate electricity. After that, the water again is channeled back to the natural course of the river as well. So this is what we are saying, and that's a good examination question, I think. So this is for example, this is the coffer dam, if we can say. And the picture should be self-explanatory. Then we can also classify based on hydraulic design. What is the purpose hydraulically? One, overflow dams, and we are talking about spillways. So an overflow dam is designed to act as an overflow structure. The I don't know where my uh, there should be some things that will allow me to write. I don't know where they have disappeared to. Uh, no, I think there's something should allow me to write. Somewhere here. They have been. I don't know. Anyway, so like the spillway is an overflow structure basically, so that if there is excess water and to maintain this integrity of the dam, and then the spillway allows excess water to flow. If you have gone to now this reminds me, I don't know how much time we have, We could visit one of these dams. At least you have a clear idea. There's Masinga. Uh, I think Masinga is one of the, and also there's Dakaini up in Nairobi, in Thika. I think in Machakos there's also a dam. I don't know what's the capacity. Yeah, so but by design, this is the overflow dam, so a spillway basically. So the surplus water which cannot be retained in the reservoir is permitted to pass over the crest of the overflow, which acts as a spillway. The overflow dam is made of material which does not erode, so that's the first thing. Because actually, some years, I think 3 4 years back, if you if you saw the flow of water from the spillway, there was some photo. I think it was doing around in the internet. You could see there is serious energy from the so if it is material that can corrode and spillway is not very far from the main dam, so then the people downstream would be at risk. So this area is designed to allow excess water to flow while at the same time does not corrode. So it has to be of very high shear strength, you know, because when the water flow exits at high velocity, highly likely it will erode. But once it starts to erode the embankment, the people dancing may be in danger. I'm sure you've seen, or you should have seen, a lot of movies. Not even movies, in fact, they are movies, but they're also actual disaster where dams have failed upstream and downstream is an entire city. People have died, and there's a lot of case studies for this. So these are the things we need to avoid. And even though the spillway is to allow excess water to flow away, the integrity of the dam cannot be compromised in either way. So we don't allow erosion. So we call that normally the spillway. And then there's what you call non overflow dams. The non overflow dam is designed such that there's no flow over it. Because there is no overflow, a non overflow dam can be built of any material such as concrete, masonry, earth, rock, fill and timber. As already mentioned, the non-overflow dam is usually provided in a part of total length of the dam. However, sometimes the non-overflow dam is provided for the entire length, and separate spillway provided in flanks in saddle away from the dam. There's a figure that shows this clearly. So you can have an overflow dam where you prevent flow completely. So on the right you can see photo on the right, or you can do an overflow in only certain sections. So within the non-overflow dam, there are some sections that will allow. The reason, if you think about it, the based on the riparian laws that we've talked about, you should not strive at the downstream of water. That's the principle. So you cannot impound water and say there's no water going downstream at all. No. In fact, before a dam is built, all these are studies that are done, and you make sure the water that was flowing before the dam was put should be the same, so that life downstream, life including people, including plants, including should continue normally. So if the amount that was flowing before you impound, the amount should continue. The amount that was there before should be continue. The amount of water should be able to sustain the life. So you cannot impound water completely. You will be taken to jail. You will be taken to court. So even when you think about impounding the water, you should still think about the downstream. So this way you see now here, even when you impound the water, you provide a spillway again to allow excess water to continue flowing down. And for those that there is no spillway, even if it's an overflow dam, certain sections you will still have to provide uh, somewhere that water can overflow so that the downstream part is life is still sustained. Okay, and so we can also classify based on the materials for construction. So we talk about masonry dam, concrete dam, earth dam, rock fill dam, timber dam, steel dam. Now, just to say, the timber dam is could be uh, temporary because timber unless treated is prone to a lot of things, especially biological degradation. So timber dams, I don't know how common they are these days, but personally, in my lifetime, I haven't seen a timber dam. So, but these are part of the, I think the during the civilization, these are what people used to use. However, they are there. So, in modern usage, gravity dams, buttress dams, and arc dams are classified as concrete dams. So, and earth dams are rock fill dams, as in back. So, actually, the most common type of dams are concrete dam, earth dam, and rockfill dam. And actually, there is the dam, rockfill, and earth, usually made of different materials, because actually a dam may not consist. Uh, well, earth dam, the because it's made of just soil, earth, and so it may not impound a lot of water. So the capacity, the heights that earth dam can go is not much, based on that limitation. Then we have combined concrete come earth dam. So it partly could be concrete and also earth, depending on different considerations. Key among them, of course, is cost. Then we have composite dam, a dam that consists of two types of materials. So we can have a rock fill and earth in some portions, and so on and so forth. And as so we can also classify based on rigidity. So we have rigid dams. These are quite stiff dams, constructed of stiff material, for example, concrete and masonry and steel. I don't know. And timber, apparently timber, well, there's hardwood, so could be stiff as well. These dams deflect and deform very little when subjected to water pressure and other forces. Then we also have non-rigid dams, and non-rigid dams are relatively less stiff compared to a rigid dam. The dams constructed of earth and rock fill are non-rigid dams. These are relatively large settlement and deformations. There are relatively large settlements and deformations in non-rigid dams. So, based on structural action, also uh, uh, eh, we can classify as shown. Gravity dams, of course, try to resist the forces by the weight, the self weight, the earth pressure, buttress dam. Sorry, earth dams. Or sorry, we have rock fill dams, earth dams. We have arch dams, buttress dams, steel dams, and also timber dams, as shown in the figure below, with the different respect to different materials for construction. So, as shown in the figure, so we could have a gravity dam made of either concrete, rubble, or masonry. Arch dam, of course, made of concrete. We can have buttress made of concrete, also timber, steel. We could also have earth dam. As you can see, also, this is the extreme right. Those are the cross section. Now, the earth dam, you can see in comparison to the rest, has relatively very low height as well. So, gravity resists the earth pressure and other forces due to its weight, we've said, or gravitational forces. Of course, because we usually talk about massive water forces, these dams are kind of expensive. You can the cost of concrete because the massive forces of the water are resisted based on the self weight. So the structure needs to be sometimes massive. So that the stability of gravity dam depends upon its weight. The gravity dams are usually made of cement and concrete. In the past, the gravity dams were made of stone masonry, but now the masonry dams are rarely constructed extent for so masonry dams are rare. This is a point, or for very small heights. Now, main features of gravity dam are generally straight in plan. Axis is straight from one abutment to the other. The gravity dams are approximately triangular in cross section. Why with the apex at the top? I need us to think why. Now, I don't know why my writing aid has disappeared. Let me try to find it. But I need us to think. Someone, tell me why you think that. Uh, why you think that this has to be triangular in shape. Anyone at random? Anyone at random? Why has this disappeared? Am I in this class alone? Hello? Class rep? Class rep? Hello? Yes, why? Why? Just a minute, okay. Just hold it right there. Please record your the attendance. I need to copy. The in Kenneth is easier. You just save. Here I don't see. Write record your attendance plus the number on the chart so that just at the end of the class it would be easy to copy, and also for prosperity I can refer. So please do that. Record. As you can see, 34 people. Some people usually say they claim they share the lab. Anyway, just record your number and name, and should be fine. Should be fine. Yes, for stability. In fact, uh, my writing aid has disappeared. But anyway, the triangular shape kind of makes the issue. You remember what we were talking about physics before? That it's thin at the top, but the thick, a little bit thick at the bottom, for stability, because so that the weight kind of the issue of the center of gravity, you know. So the wider base makes it more stable. In fact, owing to the fact that it has to resist these forces based on the self weight. So the gravity dams are generally more expensive than earth dams. Of course, I already said this, and they are quite suitable for gorgeous, steep slopes. They require strong rock foundation, of course. However, if foundation consists of soil, the height of the gravity dam is usually limited to 20 meters. Basically, this is a bearing capacity issue. If the foundation is soil, then the limitation is based on the bearing capacity issue, because You see, when you impound using concrete, and concrete has very good shear strength, and once you impound a lot of water, the water will find the weakest material and fail there. So, if concrete is very strong and the soil is weak, so when you impound, the amount of forces are increasing. So you have to limit based on the bearing capacity that is available. So the advantages, they are quite strong and stable and durable. Gravity dams are quite suitable across moderately wide valleys and gorges, having steep slopes where earth dams, if constructed, might slip. Yeah, so the other advantage is that because the earth dam, we rely on, for example, the friction. That's one of the principles that will cause stability. But actually, concrete dams, you might encase, is it that the right word? Embed it. In fact, you might embed it deep in the substrata, so that the issue of slipping is a non-issue. But for earth dams, we rely on the principle, on the friction, the interfriction between the earth dam and the foundation, for example. And sometimes when the forces are a lot, earth dams might slip. But when you realize this is the case for gravity dams, you might in fact decide to embed it deep into the rock substratum. Now, gravity dams can be constructed to very great heights provided good rock foundations are available. Gravity dams are well adapted for use as an overflow spillway section. In fact, normally the spillway needs to be aligned with a good quality concrete because of the high flow. We expect high flow and with a good enough shear strength so that there's no erosion. But that's not all. Also, every often, the spillway needs to be inspected, and if required, we need to if required we need to redo. I mean, refurbish. I should say, if there's an issue, to avoid disaster. So and then also gravity dams are suited for areas. Something is wrong. I cannot see the 90. Let's see. So here is suited for I don't know areas. Okay, you can read for that. I cannot see it. My Okay, the maintenance cost of gravity dam is low because it has good strength. The gravity does not fail suddenly. That's true. There is enough warning of imminent failure, and the value of property and human life can be saved to some extent. Yeah, it doesn't just fail. You'll see there will be cracking, there will be enough warning. In fact, this is why I'm saying there needs to be some inspection, and if there's something you can do, it's done so that human life is saved. But if in case of a catastrophe or beyond help, you'll see in enough time there will be enough warning so that people can be evacuated. Gravity dam can be constructed during all types of climatic conditions. That's no issue. The sedimentation in reservoir and the upstream of gravity can be somewhat reduced by operation of deep set sluices. The disadvantages: one, it's expensive. It has to be I'm surprised that's not the first one. But we say that gravity dams of great height can be constructed only sound rock, of course, foundation. So you need very good foundations. This cannot be constructed on weak or permeable foundations on which earth dams can be constructed. However, gravity dams up to 20 meters can be constructed. I think we already said this on weak soil up to 20 meters. The limitation is 20 meters on soil or weak ground, but for higher or the ones with massive pressures and forces, you need a good foundation. Now, the initial cost of gravity, of course, is high, more than that of earth dam. At the sites where good earth is available for construction and funds are limited, earth dams are better, of course, because of the cost. But gravity. So again, you have to balance between the cost and the usage. Gravity dams usually take longer time in construction than earth dams, especially when mechanized plants for batching, mixing, and transport are not available. Of course, you have to put when, for example, the processes are not mechanized. Once you cast, you treat, you cure, and all this will take some time, relatively longer. Gravity dams require more skilled labor. Yeah, and then also you cannot increase the height. If, for example, you did 20 and you decide that now your needs have increased, you cannot. So this is, for example, an earth dam. So an earth dam is made of earth, basically, and it resists the forces exerted upon it, mainly due to shear strength of the soil. Although the weight of the dam also helps in resisting the forces, the constructional behavior of earth dam is entirely different from a gravity dam. Main features are usually built in wide valleys, having flat slopes at abutments. The foundation requirements are less stringent than those of gravity dams, and hence they can be built at the sites where the foundations are less strong. So that's that. So so the section of an earth dam can be homogeneous when the height of the dam is not great. Generally, the earth dams consist of different zoned sections. See the figure. The impervious zone called the core. And this goes to the, I don't know whether I have said this in this class. This goes to the idea that the the materials that have good shear strength are permeable, all right, and the materials that are impermeable have low shear strength. So that is the zoning that we're talking about. So just where you need high shear strength, you have maybe the rocks or the sand, the rock fill or sand fill, because they have good shear strength. Though they have good shear strength, they have high permeability, which is not good. So in the some section immediately after the material with good shear strength, you put material of low of permeability, but they have low shear strength. So this is what we are saying. So if an earth dam is built in pervious foundation, a concrete cut off wall or steel pile line is provided for. Uh, this is like the issue of the sheet pile. Now I don't know. Uh, can I try to stop sharing again to see? I want to see if I can regain my writing, my ability to write, because it makes explaining some things easier. Let me see here. Mhm. All right. Surely there is something that should allow me to write down here. I don't know why it has disappeared. Show presenters view. Oh, here. Ah, okay. So I can get them from my right hand. Okay. So that makes it easy. So if this is your dam, what we are saying here, pen. So if this is your dam here, now where has that guy come from? Class rep, I want you to decide. Someone wants to join now. I think more than 1 hour. Someone, what do we do with him? Class rep. Hmm? Class rep. Can you be the judge? Hello? Class rep. Hello? Hello? Someone just wants to join the class now. What is your, as a fair judge, what is your assessment? No, but there has to be some seriousness. Okay. Anyway, we proceed. So this is the, so if this is your the ink color, so if this is your the dam, and if for some reason this is pervious, this is permeable, the foundation, I mean, you put some structure. Usually we do sheet pile to increase what is called the flow. So you put a sheet pile here, because the disaster would be this water here at uh, the water would want to flow there, 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 if there is no the sheet pile is not there. But once you do the sheet pile, then the water would, let me use a different color. Then the water, if it has to flow there, it increases the flow of path, what we shall say, that way. And therefore the seepage would be much less and the dam would be safer. So if the area is pervious, you can do this, increase, use sheet pile. This is an idea. Although sometimes you can also do what is called grouting, uh, or a combination depending on what is required. So still, actually, this is what I'm saying. There's still a sheet pile. This is what I'm explaining. And so the drainage filter. Oh yeah, so drainage filter. Yes, you can't see why. Why is outside the screen? Okay, so let's do now. Can you see the slides? Not there. Okay, what I was saying here is, and why is is it going outside the screen? I don't seem to understand that. But let me try to see slideshow. Can you see the screen? Hello, hello. But you can see what is on the screen. Can you see the drawing? Okay, that may not be an issue of the drawing. Anyway, what I'm saying here is, for example, this is your earth dam, and this is the, okay. Can you see the drawing there? Can you see what I'm trying to write? What are you seeing on the screen? Are you seeing? Are you seeing a drawing? Are you seeing a drawing? I think the issue is the because I'm on the next slide already, so it seems like there is some lapse between my action and uh, and you seeing because actually I'm my the drawing I am where I am now. There is a drawing, and if you say you cannot see it, then there is some internet issue. Okay, let me stop and then try again. It seems like there's some lapse between when I go to the next slide. Your screen is still frozen to the previous slide. I think that's the issue. So let me try. Can you see the screen now? You can't see the screen now. You can you see? Okay, now can you see a drawing on the screen? Yeah. So this is what I was saying that if that is your dam, and then this place, the bottom here is impervious, you put a sheet pile because the Otherwise, if this place is impervious, water will just flow like that. No, no, not sorry, no, not this way. Erase also. Water would just flow, you know, that way. Of course, you to that is what would happen. But if you put an I mean a sheet pile, then you increase what is called the drainage part, so water will go down, and so the permeability will reduce. That's the point. You can use a sheet pile. You can use a combination of sheet pile and grouting. That's what we are saying. So when we have impervious strata, then that's fine. But when you have a pervious strata, then you have to increase the drainage path to reduce the permeability. I mean the ability of water to escape to endanger the embankment. You can also see the on the diagram the safe design ratio of height, and we have said that earth dams may not the height may not go up to very far. So the height may not rise to very far because of the limitation, because you are using materials of low shear strength. They may not sustain very high loads. So the advantages, it's of course cheaper than gravity dams if suitable. Again, we are talking about the cost, uh, the cost versus suitability. So even if earth dams, even if you find that gravity dams are expensive, but that's the only option, then you have no other choice, because you cannot compare the cost of human life to the cost. In any case, it's humans that make money, and money is made to be used. So if it's absolutely necessary, even though costly, it has to be done that way. Of course, if there's an alternative that can be safely achieved, then you go for it. But if the expensive way is the only way, then of course you have no other choice. Earth dams can be constructed on almost all types of foundations, provided suitable measures of foundation treatment and seepage control are taken. Earth dams can be constructed in a relatively short period of time. The skilled labor is not required in certain construction of an earth dam. Earth dams can be raised subsequently. Yeah, you can increase the height. So this overcomes the limitation of the gravity dam that we've seen. Earth dams are aesthetically more pleasing than gravity dams, of course, because this is earth. So you might put some plants, some trees, so that it looks nice. It augurs well with the environment. The earth dams are more earthquake resistant than gravity dams. The reason for this is because they are non-rigid, like we've said. So rigid structures can take very little strain and they snap or they crack, and this is why concrete is prone to cracking. You know, but earth dams can take high amounts of deformation, and as you know, earthquakes will induce some deformation. So this is an advantage. In fact, you need when during an earthquake, you need something that can take the forces, can bend or can be flexible as the forces as it carries the loads, of course, without breaking or compromising the integrity. That's the point. Because concrete is rigid, with some strain, it easily snaps or cracks. But earth dams are a little bit more flexible or less rigid, so to speak. So the disadvantage, earth dams are not suitable for narrow gorges and steep slopes, of course, because they can slide. And also the earth dam cannot be designed as an overflow section for obvious reasons, because in fact it has to be located away from the from cannot be spillway section has to be located away from the earth dam. For this reason, this is made of earth, and when water is flowing, it will erode. So with the time, and this is basically, I'm not saying this is exactly what happened in Solai Dam, but the issue with Solai Dam, I think 3, 4, 5 years ago, water was seeping through, I think, 30 meter of impoundment, and water seeping slowly. And I'm even wondering how responsible were they? Is it the county government? Because when you see something like this, you really need to take action, because the other option is for catastrophic failure. So when you see water seeping, that's not a good sign. Action should have been taken. Yeah, so it when water flows, it means the integrity of the embankment is compromised slowly by slowly. So because of that flow, there is erosion and so many things, and the integrity of the embankment will be compromised in due course. Earth dams cannot be constructed in regions with heavy downpour, as the slopes might be washed away. Of course, the same issue of erosion. The maintenance cost of an earth dam is quite high, requires supervision. Sluices cannot be provided in high earth dam to remove slate. So an earth dam can fail suddenly. You remember the without warning or any sign of imminent failure. That's the weakness. I've given the example of Solai Dam. So these are things we have to keep in mind. So the rock dam, the is built of rock, fragments and boulders of large sizes, as shown. But you can see that's a combination of a rock fill and also earth fill. And the idea is we need to take care of permeability, because if you put rock or sand, they have good shear strength but have very low permeability. So most likely your embankment will be washed away. So usually we put some clay core, as you can see in most of the figures. So the main feature is an impervious membrane is placed in rock fill in upstream to reduce seepage. I've said this. The membrane is usually made of cement. Okay, yeah, could be made of, because you want to reduce permeability, so could be made of cement, concrete. So the good thing with concrete has good shear strength and also has low permeability, or sometimes made of clay, depending on how much on the course. Membrane is usually made of or concrete or asphaltic concrete. Here we say that dry rubble cushion is placed between the rock fill and the membrane for distribution of water load and for providing support to the membrane. Sometimes the rockfill dams have an impervious earth core, yeah, in the middle to check seepage against the instead of the impervious upstream. Yeah. So I've said we need impermeability. So if you want to use, depending on the need, yeah, and the money at hand, you can use cement, concrete, or you can also use clay, which has low permeability as so the earth core is placed against a damped rock fill. It is necessary to provide adequate filters between the core and the rock on the upstream and downstream slides of the core, so that the soil particles are not carried away and piping does not occur. I think I've said this often. You don't, because the carrying capacity, that's the ability to erode. So filtering means that you have a system such that the large particles can trap small particles and sorry, small particles can be trapped by large particles and so on and so forth. Just like kind of sieving, now the particle sizes sieve themselves so that you avoid piping and of course erosion. The slope slides of rock failure are usually kept equal to the angle of the repose of rock, which is usually taken as 1.4 to 1. The angle of repose is if you pour, if for example you are to pour, okay, let me use a simple example. If if you are to pour sugar or salt or flour, cooking flour, to make a heap, it will uh, all of those things will form something like this on your table or wherever. So the angle of repose is this angle here. That's the angle of repose. Of course, should be the same for the two sides. That's the angle of repose, and has something to do with the angle of friction. But that's besides the point. So the slopes have should have something. If you are to pour the rocks freely, the height they will form, that should be the natural height or the natural slope when you construct a dam. This is an earth dam, and this is the reason why you can see that earth dams cannot go very long, because if you want, if this, you can see this ratio already, 1.1 to 1.4, 1 to 1.4. That means if you want to go a very large height and the slope is not a lot, then you need a very large area, which might be impractical in certain instances. So that is what limits the height, because then, because of the ratio of the height to the horizontal extent, then you need a very large area for for a rock dam that should go to high heights. Rockfill dams require foundations stronger than those of earth dams. The foundation requirements are usually less stringent than those for gravity dams. Rockfill dams are quite economical when large quantity of rock is easily available on site. Advantages are quite inexpensive if rock fragments are available. Rock fill dams can be constructed quite rapidly. Rock-fill dams can better withstand the shocks due to earthquake than the earth dams. Rock-fill dams can be constructed even in adverse climatic condition. Disadvantages: rock dams require strong foundation than earth dams. Rock-fill dams require heavy machines for transporting and dumping, compacting rocks. You need heavy machines, because you're dealing with boulders, you're dealing with rocks. You need an effective way to carry them. So we also have this an arch dam. You can see it looks like an arch, and the reason for this is you can see it's already carved. So if the water pushes, it kind of tries to straighten the arch, uh, and so the load is effectively carried. This is the same idea with pre-stressed concrete, right? You provide some pre-stress, and in service, you provide some, because the pre-stress is negative, for example, then you apply positive stress, then the positive stress you applied in service cancels out the negative stress that was already applied inside the concrete. And so for all intents and purposes, the concrete in its lifetime is carrying loads, but the loads are close to zero. So it feels like it's experiencing zero stress, and this controls deflections, as yeah, deflections, and also ensures serviceability of your concrete structure. So this is the same idea. So this is already carved. When it's carved, it seems like it is carrying tensile forces. And then when the water presses, because water wants to flow away, it presses against the arch dam, giving it compressive forces. So tensile forces minus compressive forces are either zero, or it will carry a very low forces, and hence ensures, no, not low forces but low stresses, and ensures the longevity and long-term service of the arch dam, so to speak. But arch dams are basically gravity dams in any case. So an arch dam transfer the water pressure on forces mainly the abutments by arch action. Arch action is the compression, the compressive, because we know concrete is good in carrying compressive forces but weak in tension. So that's why you already in pre-stress concrete, you already you give it negative forces or negative tensile forces, and then when you apply compressive forces, then the tensile and the compressive forces cancel out. The net effect is we have zero stresses, or our stresses close to zero, and the concrete will do well in service. So an arch dam is quite suitable for narrow canyons with strong abutments which are capable of resisting the thrust produced by arch action. The section of an arch dam is approximately triangular like a gravity dam, but the section is comparatively thinner. The arch dam may have a single curvature or double curvature in the vertical plane. Generally, the arch dams of double curvature are more economical and are used in practice. The quantity of concrete required in arch dams is less than the uh, is less than that for gravity dam, but it's not necessarily less expensive because of the high cost of concrete formwork. Because actually you can see the arch dam is okay, kind of, I think, beautiful. The shape looks nice, kind of carved. Now to put formwork that can do that kind of can create that kind of shape appears to be so even though the amount of concrete required is even though it appears the amount of concrete required is less, but the cost of the formwork. So the arch dams are not necessarily less expensive than gravity dams. The arch dams are subjected to large stresses because of changes in temperature, shrinkage of concrete, and yielding of abutments. The arch dam requires good quality concrete for resisting stresses. So advantages: requires less concrete as compared to gravity dam as the section is thinner. Arch dams are more suited for narrow V-shaped valleys having very steep slopes. The uplift fresh pressure. The uplift pressure is not an important factor in the design of an arch dam because the arch dam has less width, and the reduction in weight due to uplift does not affect the stability. One important thing we talk about, these are hydraulic structures which you have to think of uplift. So if you have a very wide area here, and water is, of course, what I think we already talked about this, water would tend to, this is your, and water wants to flow this way, there will be uplift forces because water is flowing there. So So that has something to do with the width. So the higher the B, the more these uplift forces. If it's very thin, if for example, it just then the uplift forces are less. So this is what we are saying. So massive for concrete, for rock dams, you need to also consider the uplift force. Otherwise, for arch dams, this is not an issue, because the base, the width of the base is not much. Now, an arch dam can be constructed in a relatively less strong foundation. A small part of load can be transferred to the base, whereas, so again, we are talking about the base, the size of the base, because again, again, depending on the size of the base, the forces, if is force over area, pressure here is force over area there, and then versus just a small area like this, then the forces, so F1, let's call it F1, and the forces here F2. Of course, F1 is much greater than F2. So this is for the uplift forces. Again, the uplift forces is counteracted by the self weight again. So let's the self weight. So the self weight here is more than the self weight, and the self weight has to be carried by uh, the the foundation again. So for arch dam, because the section is thinner, we talk about the foundation requirement is not as stringent in comparison. Now, the disadvantages of arch dam requires good rock flanks and abutments to resist the thrust. If the abutment yield extra stresses develop which may cause failure. The arch dams actually requires this. I thought that this was should have been the first disadvantage. In fact, these arch structures are quite beautiful. They look beautiful, but quite difficult to construct. Actually, for the engineers, the architects like these fancy looking designs, mostly by arches, look very fancy, very nice. And first, they cannot carry a lot of massive. How can I say? What can I say? The first issue with them is they are very difficult. The constructability, they require sophisticated formwork to carry, and then they require a lot of space, and also require a lot of skill. So while the architects normally like these fancy things, but the constructability is a challenge. Now, the arch dam cannot be constructed in very cold climates because of the swelling of concrete occur due to freezing. The Because of the complications, of course, because you need skill, you need complicated formwork. The speed of construction is relatively slow. Again, for the expansion of concrete, you can see that the curve. So if there is expansion of concrete, then there might be if there is expansion of concrete, there might be so if there is expansion of concrete is a problem, because that would also the dam is constructed already in a confined place. So if there is expansion, then we don't there might be cracking. If there is expansion, there might be you need to allow the space for the extra uh, for the expansion, for the extra length. Otherwise, if it is constructed in the fixed volume, Then due to the cold weather, the swelling, of course, the concrete will crack. So this is we don't need this. And then we have buttress dams are of different kinds, deck type. Let me see how many. Actually, I have another appointment. Discard. Let me see what is outstanding. Yeah, I think we can finish this. That's not a lot. Okay, let's. Yeah, I think we can finish this. Okay, so the expansion issue is also a big issue because when when concrete will expand in a confined volume and there's no space, concrete will crack. Now, buttress dams are of three types. You have deck types consisting of sloping deck supported by buttresses. Buttresses are triangular concrete walls which transmit the water pressure from the deck to the slab. I think we'll see diagram next. Buttresses are of compression members as shown in the figure. Multiple arch type. The deck slab is replaced by horizontal arches supported by buttresses. The arches are usually small span and made of concrete as shown as already you can see here. So this is multiple arch buttress. This is the deck type. This is the buttress we are saying. This is the buttress and you can see this is the deck. So the buttress transfers the this is what we are trying to say here. The transmit the water pressure from the deck slab to the foundation. So uh, so you can see the slab is this. So let me use the slab is that, and this is the deck. So this is the cross section. So the buttress, sorry, this is the buttress. So the deck and the buttress. The buttress helps with the transfer of the load to the foundation. So you can see the cross section there. So massive head type. There is no deck slab here. There's no deck slab. Instead of the deck, the upstream edges of the buttress are flared to form massive head. Note the buttress dam requires less concrete than gravity, but they are not necessarily cheaper because of the extra cost of the formwork reinforcement and more skills that are required, more skilled labor. And then we have steel dams. One very common is the sheet pile. Steel dam consists of steel framework, which steel skin plate, and it is upstream face. Steel dams are generally of two types. So these are some very watertight. So like I said, you remember when I say when you put earth dam, and then I said if you have impervious rock, then you might add sheet piles because they are watertight. This is a point. A direct started steel dam, the water pressure is transmitted directly to the foundation through inclined struts, and then just a minute, direct. So some repetition there. And then cantilever type, steel dam, there is a bent supporting the upper deck, which is formed into cantilever truss. This arrangement introduces tensile forces in the deck girder, which can be taken care of by anchoring it into the foundation at the upstream toe. Direct started and cantilever steel dam as shown in I think is better explained with a figure. Okay, so this is the figure for deck type, but so direct started and cantilever, still. So the first one is direct started, and the second one is cantilever. And this is what we see, that the danger that the tensile forces are induced can be easily transferred to the ground, as shown. So the steel dam is quite costly and subjected to corrosion. These dams are almost obsolete, we say, and steel dams are sometimes used as temporary coffer dams. Of course, but if you have to use them, for example, like the sheet pile I've talked about, you have to treat them. You have to take care of the issue of corrosion, and so on. So you must there has to be some treatment to make sure that they can uh, they can be have good service life. Now, timber dam consists of framework made of timber planks. These dams are mainly of three types. Frame type, the stability depends on the water in the deck and upon anchorage of seals. The structure of this dam is as shown. Uh, we add rock-filled crib rock of timber members. Cribs of timber member are drifted, blotted uh, together, and then the bottom members of the crypt are generally pinned to the rock foundation. The space between various members is filled with rock fragment to give stability. Of course, the rocks have some weight in comparison to timber. So to anchor the whole structure and give it stability, you add some rocks. So there's the beaver type. This is like the beaver. Uh, there is an animal called the beaver, if you know, and likes to make things like this. So consists of timber members of round section forming as spacer logs, forming bends. Spacer logs are placed between the butts and drift pinned together, pinned to other logs. The bottom members are fixed to the foundation uh, uh, anchor bolts as shown. So that's the beaver. So the advantages that these dams are generally used as temporary dams. They short life, but if well designed, designed, construction and maintained, I think if well designed, constructed and maintained, they may last even for 30 to 40 years. The timber dams are used at places where timber is available in plenty, and the height of dam is low because of shortage of timber. These dams are becoming obsolete. Selection of dams. So this I think this is something we talked about already. How to select a dam. I think just trying uh, to to remind you. So I think that we'll end there. And this is just showing you the uh, suitable conditions that you can factors that suitable factors that favor the location of a dam, and also some uh, hazards or places that you shouldn't consider for a dam, like faults. I think you read there, and also some salient feature or the morphology or something, some requirements, some basic requirements for a dam that or some basic things that have to exist in a dam. So otherwise, I think we shall end here. I will send the notes to your class rep unless there's a question. I need to give you assignment for the because this course 60% of it is design, which I think I will have figured out for the next class in the next by the next class. So unless there's a question, class rep, we can end here. I will send you the notes. I have another appointment. If I forget, please you have to remind me. I have another appointment and also have another class immediately. Class rep, is that okay? Hello? And please make sure you have recorded your attendance as on the call box. Class rep. So you are attending class and also doing other things, right? Okay. Yeah. So the class is did you hear what I said? No, we will end the class. I will send you the notes. If I forget, you remind me. And I need to give you because this course 60% of it is design. I will need to give you the design. But when are you doing your exams? December 13th. Okay. Okay. So you still have some time. Okay, very well. Okay. Sawa sawa.